Hello there, and today I'm going to be talking through a Mechanics 1 Moments question from the Edexcel past paper in January 2012. And if you have that paper to hand, it's question 4. Now, this is a moments question where they've given us the information and a diagram to go with it, but I always draw the diagram again to include the forces, just in case if you were to do it on this one and make mistakes, it could get quite messy. So I'm just going to start by drawing my uniform rod that is going to go from A to B. So I'm just going to start by drawing it underneath here and reading the information that they have given me. It's a non-uniform rod. This is the first bit of information that stands out. So it's going from A to B. Now, the fact that it's a non-uniform rod may confuse some students, but in the context of this question, all it means is that the mass of the rod doesn't act in the middle. It will act somewhere other than the middle of the rod. Now it tells us that the mass is mass M, and it has a length 5d as shown in the original diagram. It rests horizontally in equilibrium on two supports at C and D. So if I draw a support here at C, AC is a distance little d, and there is another support here at D, where from D to B, again, that distance is the same as A to C, which is a little d. That's just using this information here. Now the centre of the mass is at the point G, so G is here, and this is exerted downwards. So this mass of M exerts a force of M times G, where G, as always, is equal to 9.8 newtons. And a particle of mass 5/2m is placed on the rod at B. So if I was to draw the particle there at B, then this will have an arrow pointing down, and the mass of 5/2m will produce a force of 5/2m times G. Now finally it says the rod is on the point of tipping about D. Now what that means is the rod is at D, it's about to tip over. Okay. Now that's significant for this question because it means that the reaction force on the rod from the support at C is 0. It basically means this rod is only just touching the support, but it's not resting on it, so there's no reaction force upwards. So the only reaction force upwards is on the rod at D, and I'm just going to label that R. Okay, so that's our diagram drawn. The question wants us to show that the distance GD is 5/2d. So the distance from G to D, which I'm just going to label here with an X, is equal to 5/2 times D. Now what I'm going to do, given that it wants the distance of G from D, is I'm going to take moments about this point D. And the nice thing about doing this is it means we don't have to worry about this reaction force that we don't actually know. If we take moments about D, then that won't be in our equation. Because remember, moments is the magnitude of the force times the distance from the point where you're taking moments at. So I'm going to make it nice and clear for the examiner what it is that I'm doing. I'm just going to write moments at D. And what I'm going to do is, because the rod is in equilibrium, so I'm going to equate moments that move the rod, or that act in a clockwise direction, with forces that act in an anti-clockwise direction. So the two forces that we're looking at is the weight of the rod G acting in an anti-clockwise direction, and the weight of the particle acting in a clockwise direction. So I'm going to do the weight of the particle is equal to 5/2 mg, and I'm going to times that by D because it's a distance D, small d, from the point D on the rod. Now that's the moment acting in a clockwise direction, I'm going to set this equal to the moment acting in anti-clockwise direction. And that's going to be coming from the weight of the rod mg acting at a distance x from the point D. So this will contribute a moment of weight mg times the distance x. Now, if we were to cancel out m and g from both sides, so dividing both sides by m and g, that simplifies to 5 over 2 d equals x. So my distance x, which is equal to gd, is 5 over 2 times d. And that is exactly what they wanted us to prove. Now, in terms of how the mark scheme allocates marks for this, obviously this is a 4-mark question. You would get 1 mark for taking moments at D, and you would get that's a method mark. And if you did this perfectly correctly, you would get an accuracy mark. Now, knowing to cancel out those factors to find the value of x is a second method mark, and getting the correct answer is your final accuracy mark. So that's how the 4 marks are set aside for this part A of the question. Now, for part B, the particle is moved from the end B to the midpoint of the rod, and the rod remains in equilibrium. So the situation has now changed, and we have to find the magnitude of the normal reaction between the support D and the rod. Now, because the situation has changed, I'm going to draw another diagram from scratch to show how it has changed. And drawing diagrams really is just going to make our life a bit easier. It's going to make it a little bit less likely for us to make mistakes. So we are still looking at a rod that goes from A to B. We still have these supports at C and D, and this distance from A to the support C is little d. This is the same. Nothing has changed in this respect from the first part of the question, and the weight of the rod, remember it's a non-uniform rod, still acts at G, so that there is mg, and the mass of the particle, which is now in the middle, also acts down, and that's going to be 5 over 2 mg. Now, in terms of distances, I know that the distance from G to D is 5 over 2d. So in other words, this is 2.5 d. And obviously if this is 1d and that's 1d, then that makes this distance here between C and G, that's equal to 0.5 d. Finally, obviously, because this rod is resting on 2 supports, there's going to be reaction forces. Now, because it hasn't specified that the rod is on the verge of tipping, we have to assume that there is a reaction force at both R and D. Now, because it hasn't specified that these are the same, we also have to assume that they are different. So I'm just going to label the reaction force at C equal to RC, and the reaction force at D equal to RD. So this is my diagram now to represent this new situation, and what we have to find is the normal reaction between the support at D and the rod. Now, the only thing here that we don't know is RC and RD. Now, because we are only asked to find RD, so the reaction between the support at D and the rod, we don't need to find RC. So if I was to take moments about C, not only would that eliminate RC, we wouldn't have to worry about it, but it would also give us an equation allowing us to find RD. So I'm going to make it clear. I'm going to say moments at C, and same as always for a rod in equilibrium, I'm going to set the moments acting in a clockwise direction equal to the moments acting in an anti-clockwise direction. So in a clockwise direction, I have the mass of the rod, which is mg, and that's a distance of 0.5 d. So I'm going to put that into my equation. I'm going to have 0.5d times mg. That's for the weight of the rod. And I'm also going to have the force of the particle acting. Now this is 5/2 mg, and because this is halfway along the rod, and this distance is d and the total length is 5d, the distance between C and this particle must be 1.5d, because it's it tells us that it's placed in the midpoint of the rod. Remember, the total length is 5d. So the force from the particle will contribute another moment acting in a clockwise direction, and that is equal to 1.5d times 5/2 mg. Now all of this is equal to the moment acting in an anti-clockwise direction, and that's the reaction force at d. Now remember, the distance, because this distance here is d, from d to b, and the distance from A to C is also d, then the distance from C to d is 3d. So this will contribute a moment of rd, that's the reaction force, r with a little subscript d, times the distance 3d. Now if we were to just simplify this equation a little bit, that will give me a half mgd plus, if we work this out, that will give me as a fraction 15/4 mgd, and that is equal to 3d r subscript d. That's just the reaction force at d. Now simplifying this left hand side, it will add up to 17/4 mgd equals 3d rd. Now because we have a factor of d on both sides, I can divide both sides by d and cross that off. And if I divide both sides by 3, then that tells me the reaction force at d is equal to 17/12, that's just dividing this by 3, times mg. And that's the answer for my reaction force at d. Notice I took moments about C because that allowed me to eliminate, not worry about the reaction force at C, and just concentrate on the reaction force at d. Now in terms of where the mark scheme allocates marks here, you get 1 method mark for doing a correct moments equation. Taking them about C, like I said, allows you to do it all with 1 equation. And if you get the equation fully correctly, that is also 2 accuracy marks. Now knowing to rearrange and solve this to find this value of rd, you get 1 method mark for solving it and a final accuracy mark for getting this correct answer, which gives you a total of 5 marks for that part B. So that was the Edexcel Mechanics 1 past paper question 4 from January 2012 paper. Thanks for watching. I hope to see you again sometime soon.